We propose a novel gesture recognition method EarHover that enables mid-air gesture input to Hearables. A currently available hearable often comes equipped with capacitive sensors, pressure-sensitive sensors, or physical buttons. These sensors require hands-on input to the device. However, it can be challenging when hands must be kept clean, such as eating. In this study, we propose a method to recognize mid-air gestures performed near the device. Our method focuses on acoustic signals that leak outside the device during acoustic signal playback in order to expand the variety of operations beyond touch. This study utilizes the Doppler effect of sound leakage signals to recognize mid-air gestures. When the user moves a hand around the ear, the tone signal is reflected by the hand. The frequency of the tone signal changes according to the speed of the object. The system records the sound leakage signal during gestures and converts it into a spectrogram image. The spectrogram image is applied to a gesture detection model, and the data determined to be gesture motion is used in a gesture classification model to estimate the type of gesture. The training of the gesture classification model involves color bar adjustment and image stretching data augmentation. Finally, the gesture is determined. We implemented the in-ear device and the open-ear device. Since microphones in commercially available earphone-type devices are internally low-pass filtered, we attached another microphone to a commercial earphone. We conducted 4 experiments: gesture selection, auditory impact, gesture detection, and gesture classification. First, in gesture selection experiment, we designed 27 mid-air gestures for EarHover, referring to the user-defined gestures derived from the gesture elicitation study around the ear area. We formulated a set of gestures for EarHover based on 3 criteria: Doppler shift magnitude, Doppler shift similarity, and usability. We quantified these criteria and sequentially extracted gestures. Finally, we selected 7 gestures. Using these gestures, we evaluated EarHover's performance. Second, in auditory impact experiment, we investigated the auditory impact of using EarHover with music playback on the user. We created 3 test music by applying a filter to remove the frequency band affected by the Doppler shift and then synthesizing it with the measurement signal. Participants randomly listened to the original and test music without prior knowledge and were asked whether they thought the music differed. We found that the influence of EarHover on music application is minimal to conduct statistical tests. Third, in gesture detection experiment, we measured the daily activities to detect the gesture. We set up 11 different tasks and movements that are frequently performed in daily life. The average false detection rate for daily activities was 2.5% for the in-ear device and 1% for the open-ear device. The average false detection rate per gesture was 10.6% and 10.7%. Finally, in gesture classification experiment, we collected data each from 2 devices in an environment of stable, with a glove on the right hand, with a person sitting to the right, which the participant is walking, and which participant is listening to the music. In stable, results showed F-score of 79.7% and 85.9% for 7 gestures with in-ear and open-ear device. In many other environments, by ingeniously configuring the model, achieved an F-score equal to or greater than that of the stable, thereby attaining high accuracy throughout. This is a use case of EarHover when the user is cooking. The user can perform gesture input while the user wants to keep the hand clear. This is another use case when the user is gardening. The user can perform gesture input while the user is wearing gloves.